So I'm Daniel, and I work at Optibus, and I will tell you about some classic problems in public transport optimization, which is vehicle scheduling and crew scheduling. Okay, maybe to give you a big picture, so you can roughly divide all the public transport problems. It's a bit too rough, but you can do that. And the strategic planning part and the operational planning. So we heard some strategic planning before, which is more the long-term planning. So you want to design a public transport network from scratch. So it's the long-term decision that you take. So line planning, for example. And then the other thing is, which is, I think, more common in practice, is the operational planning. So this is the day-by-day planning. So how do you plan a single day, a single week? There is more common to use optimization. So I think almost all big public transport companies, they do some kind of optimization here. That's what I will talk about. So one thing is vehicle scheduling. So how do you schedule your vehicles, your buses, your trains, whatnot? And the other thing is duty scheduling. So it's basically how do you assign the people to the buses? Where do you put the drivers? Since it's called OptiBus, right? I will only talk about buses, which also happens to be the most used public transportation mode in the world. But in principle, you also have these problems for trains. They just look a bit different. Okay, so let's start with vehicle scheduling. Okay, don't get afraid. There's a lot of stuff on the slide, but basically it's quite simple. So it's we are talking about buses here. So typically what you have, right? In Berlin, you have a lot of buses, and all of the buses have to go their trips, right? So they start at a certain point at the departure terminal, so where they start, and they make their trip, and at the end they're at the arrival terminal. Then of course you have a lot of buses, and then the problem is basically which way do the buses go? Where do they start? Where do they end? And when they end, of course, they can make another trip. So let's give me an example here. For example, here we have four trips. So these are the 4 trips that I need to cover, which means the first trip starts at 10 and finishes at 11. And it goes from terminal A to terminal B. Then, of course, the thing is, okay, if I have a bus now that does this trip, so it goes starts at 10 at terminal A, and 11 it's finished at terminal B. So I could put the bus back to the depot, or good, but of course, it would be nicer if I can use the bus for the next trip. And then, for example, here, right, so the trip is finished at 11, and then I possibly have time to start this trip, which starts 11:45. And here you need what is called a deadhead trip, which means a trip without passengers. So when I'm finished with my service trip, where I have the passengers, then I want to possibly make another trip to do my next service trip here. And then there's what you need, what is called compatible, which is very simple. It just means if I do 2 trips, one after the other, that I have time after I finish my first trip to start the next trip. So these are just a thing here. So it's just a bit more fancy notation. It's very simple. So when I'm finished with one trip, do I have enough time to start the next trip? Because I need to go with my bus from the end terminal to the start terminal of the next trip. So in this example here, this is just the time you would take to go from one terminal to the other. So I'm finished at 11. I'm at terminal B, and the next one starts at terminal C. This one I want to go, and I look, okay, from B to C, I have 20 minutes. So I stop at 11:45. I'm on time to do that. So in this case, the trip 1 and 3 would be compatible because I have enough time after finishing one to go to the other one. So it's very simple. It just looks a bit complicated with all the numbers. Then here's a bit of math, right? So again, it's not really important. It just means when I have a sequence of compatible trips, so it means I can do the trip, afterwards I can make the another trip, and so on. That's basically what a bus can drive. Then I call it a vehicle block, which is very one course that a bus takes, which is feasible. And then I say that a vehicle schedule is a set of blocks that covers all my trips, all my service trips. So all the trips that I want to take, they are covered. I think it's a bit nicer to see it in a graph view. So here we have the 4 examples that we saw before. So we start at 10 and we finish at 12:45. And we have these 4 trips here. This is the first, the second, the third, and fourth, right? So this one starts at 10 and finishes around 11. Then we have another one that starts at, I think it was 10:30, 11:05, and so on. So these are the 4 trips I have to cover. And this is the timeline. And here we have the depot, basically where the buses start. To make it a bit easier, I have two depots here, but it's just for representation. In the end, it's the same depot. So basically, the buses start from here. They can go to one of the server strips, and then at the end, they have to go back to the depot, which looks like this. So from the start of the day, I could go to all depots. Sorry, from the depot, I could go to all trips. And whenever I finish a trip, I can go back to the depot. Or in some cases, if it's compatible, when I finish a trip, for example, this one, I could go to the next trip. Because here I have enough time to go to that trip. Same here. If I finish this trip, I have enough time to go to that trip. So they're compatible. And then one schedule would look like this. So I have 3 vehicles in different colors. The red, the green, and the blue, which would mean, okay, my red vehicle starts this trip here, stops here, and then it has enough time and also covers the next trip. So this is one vehicle that does 2 trips. The other ones, they just do 1. So they do 1 trip and then they go back to the depot. And what you can already see here that the graph is acyclic. So there are no cycles because it's like it goes over the timeline. So you would never go back in time. So you don't have cycles in this graph. And this is called single depot vehicle problem because you only have 1 depot, which I kind of copied here. Okay, and then you can look at this in a more graph theoretical way. So you see we have a directed graph here, we are acyclic. So now we have the graph view here. So a little bit of formulas. So we have a directed graph, vertex set, and an arc set, directed edges arcs. As I said, we have a directed acyclic graph. And we say, okay, we have the vertices consist of our of all the trips that we have to cover, plus these S and T, which is basically the depots that we saw before. So this is the depot that I had on the left-hand side. This one, and this is the T. So this is this typical ST that you have for notation. We start from S, we want to finish at T. And then we say, okay, basically this notation just means from the start depot, we can go to all trips. And this means from the end depot, we can also, sorry, from all trips, we can go to the depot again. And one thing is here, we consider these trips here as vertices. So if you use it as a graph, there's no need to have it as an edge. You can just take it as a vertex because you only have incoming arcs here and you only have outgoing arcs here. You can just contract them and you consider all these trips that you want to cover as single vertices, which would be the T's here. And then of course you have costs, arc weights. So typically what you would do is you would set a higher arc weight on these arcs here because they tell you how many vehicles you need. Because every vehicle has to take exactly of one of these outgoing arcs. So if you have a high cost here, you minimize the number of vehicles, which is normally the most expensive part. Okay, and then there's the problem. For each arc, you have a binary variable, 0, 1. You want to minimize the cost. And here you have some kind of flow problem. It just tells you, okay, incoming flow has to be equal to the outgoing flow. And at for each trip, the incoming flow is 1, which because your binary means for each flow, there's exactly 1 incoming variable, so 1 incoming vehicle. And because this is 1, the outgoing also has to be 1, and then we get some pairs here. So in the end, everything decomposes into pairs, how we see it here. I guess that's like a standard formulation. So this is the classic problem. So for each arc, we have a binary variable. Then we have some kind of flow constraints here. Just make sure that we really have paths to the graph. And then we say each trip has to be covered. Okay, and this problem is, I guess most of you know, it's a min-cost flow problem. It's a very classic problem. The matrix is totally modular, so then you can just solve the RP and you are done. That's why it's a polynomial type solver. So this problem is kind of easy. Also actually in practice, because you have a lot of very fast min-cost flow implementations. Okay, so unfortunately, in the real world, it doesn't look like that. Typically, you have far more constraints. The next step in literature is usually that you consider several depots, which means not all the buses start at the same point, but you have several depots over the city, which in Berlin, you have a lot of depots where the buses start and where the buses can end. And then it gets already more complicated. So you have basically the blue buses that start from this depot, and you have the green buses that start from this depot. Then again, we have the copy here. And then essentially we have two disjoint graphs. So we have the green graph to go somewhere here, and then we have the blue one. So the green is everything that can be covered by the green buses, And the blue one is everything that can be covered by the blue buses. And then we have a multi-graph because we can have parallel arcs. For example, this deadhead here could be done by a green bus and by a blue bus. Okay. Yeah, maybe it doesn't look much more difficult, but actually it is. So just shortly here the formulation. I guess the intuition is the important thing, right? I just want to write the math down. The important thing is just that you have several sets of depots, and each depot we would just say that is a fleet. These are different kind of buses. So before we had the green buses and the blue buses, and then we have some kind of capacity on a number of buses for each fleet. And yeah, the notation looks a bit more complicated, but it's just what we saw before. So we have a directed acyclic multigraph now. And then here again you have the trips, and then you have different S and Ts. For each fleet you have a different one. And there's not just some notational stuff, which is not super important. So the important thing is just to remember we have several disjoint graphs basically. For each graph corresponds to one fleet, to one set of buses that start at the same depot. And again, you have some arc weights here. So what do? We take the union of all our arcs, which is our set A. And then for each, we have a binary variable. Again, we say 0 if we don't take, 1 if we take it. We want to minimize the cost at before. Now the constraints look a bit different. So here we have these flow balance constraints. We have them per separate graph. So we look at all the different fleets. So before we had the green and the blue fleet. And for each of the fleets, we have to have the flow balance constraints, which means that if a blue bus covers one trip, then the blue bus also has to go out of the trip. If it goes into the arc, into the vertex that corresponds to the trip, it also has to go out of it. So it's just that you have these separate graphs here. As before, we have this constraint which tells us, okay, every service trip has to be covered. So for each service trip, so for each trip where passengers are on board, there has to be at least one incoming arc. So there has to be one bus that does this trip. And this thing here is just the capacity constraints, so that you don't take more than kappa F many of the buses. So it's similar to before, right? Only that you have it here with that you have these constraints basically which go over several graphs. But even though it looks similar, already for two depots, this problem is NP hard. The thing with one depot was polynomial solvable, and this thing becomes already NP hard. So which is kind of a classic result with some multi-commodity flow in the end. Okay, so how do we solve these problems? So we saw the formulation. How do we solve it? So what you can observe that usually you have far more variables than constraints, which is just because you can have a lot of deadheads. So it's in the quadratic order basically. Because when you stop a service trip, you can go to a lot of another service trips. That's the first observation, that you have a lot of variables, and in the end you don't need so many of them. So then what obviously comes to mind, I guess, it's like you do some kind of column generation. So you don't consider all of them, but only a few of them. And the other thing that we saw, right, that we have these min-cost flow subproblems. Now we have different graphs, but still on each of the graphs we have basically a min-cost flow problem. Okay. So what maybe comes to mind is like a very simple idea. It's what is called static column generation or sifting. I think CPLEX call it sifting. I think Shriver called it static column generation. I heard it somewhere, this term. So let's do the following, right? We say, okay, we have too many columns. Let's say A is our set of columns. So this is all the variables basically. And then we say, okay, we do something a little bit like a simplex, right? So it's basically like a primal simplex, a bit extended. Let's say we're able to start with a subset A prime of A that contains the feasible solution. So we have a primal feasible LP solution that just lives in this A prime. All the other ones are set to 0. So for example, we can get them from an IP solution. So in these cases, often you can run a heuristic, a primal heuristic, then you get an IP solution, and you just take all the columns from the IP solution. On there, you can create a feasible LP solution. So we have some subset A prime on which we have a feasible solution. It's something like with if you have a primal simplex, you could just take the start basis, which would give you the set. Okay, then we solve the RP. Then we have a feasible solution on A prime. All the other columns we can set to 0. We compute a reduced cost, how you would do it in a primal simplex. If you see all the other columns have reduced cost 0, we are converged and we can stop. If not, we will do something similar to the primal simplex. Yeah, we just add some columns with negative reduced cost to A prime. Yeah, so it's very similar to primal simplex. Just here you can add a lot of columns instead of just one. Looks kind of too easy to work, but there are actually cases where this kind of approach works. So Cplex, for example, has sifting, which is kind of similar to that. Okay, in our case, it doesn't work. It converges very slowly. The problem is that we are missing the path information here. So if you go back, and maybe the reduced cost, for example, on let's say on this guy, are very small, so very negative. We say, okay, we add this guy to our set of to our master problem, so to say. But if you don't have, for example, this one here, it doesn't really help a lot, because then the master problem is never able to really build the path here. So this is kind of the problem what is missing there. We're always missing the path information. So just adding single variables with forgetting about the structure here, forgetting about the path, doesn't work well, because then we have to add a lot until we really have the full path in our master problem. So I just want to review like a classic, or like, maybe not classic, but a bit older approach, like almost 30 years old, due to Andy Loewe, which I think nowadays is not really used anymore, but we were still looking at this. How do you approach now? We saw before that we have these min-cost flow subproblems. So let's review again our problem. And what we now do is we do a Lagrangian here. I guess most of you know what a Lagrangian is. Maybe I will shortly explain. So basically what you do is we take one constraint and put it into the objective, which was this constraint which told us that for each service strip, you have to have at least exactly one incoming arc, which would be this one here. So these guys always have to be equal to 1. And then we put basically this guy into the objective with some weight. For each constraint, we have a weight P, T here. So this is a classic Lagrangian. Why does it work? So basically this guy here, no matter which P you take here, underestimates the actual LP value. Why is that the case? Because let's say you have an optimal LP solution to your original problem, then this constraint here would be satisfied. So this would be exactly 1. So we have a minus here. And then it would always be 0. So whenever the original formulation is satisfied, then this guy is basically 0. Which means we for sure have this solution also to this problem, but we might find a better solution. That's why there's an underestimation to problem. And I mean, this is basically some generalization of the LP duality that we have. And also, if we were to take an optimal dual solution to the original problem and just take the corresponding P in here, that would be an optimal one. So basically, what you want to do here is we want to max the P, right? We want to get this one as close as possible to the actual LP value, which we do here. Okay, so we have this problem. Why is it nice? Because here we see as before, we have again some we have independent min-cost flow problems. We see everything here just works on the separate graph. So for each f, we have a separate graph, and all these constraints are just on a graph, on this f graph. So this decomposes into cardinality f many separate problems. Problem is Lagrangian approach is difficult to solve, right? So if you want to solve this from scratch with bundle or whatnot, it doesn't really work well. But here we have one subproblem, which kind of still catches the network structure. Okay, this is the one subproblem. What we could also do is we put another constraint in the objective, namely this one, which the flow balance constraint, which tells us that the incoming flow has to be equal to the outgoing flow. So it's same idea as before. Just the Lagrange works on a different constraint. And again, we have the penalization here. again, this one here is a min-cost flow problem. Yeah? Because we have the incoming flow has to be 1, we have the outcoming flow has to be 1. This works on all arcs, but still is a min-cost flow problem. Okay, what is nice about these things is, even if you don't do the Lagrangian, if you were to have an optimal dual solution to the original problem, this one would also be solved optimally, to optimality. So this would be enough to solve it by strong duality. Okay, and then what we do now with these two problems, so we have these two different problems which kind of capture our network structure. We again do this simple sifting approach that I saw before. So we have a multi-depot weaker scaling problem with the column set A. We want to have an LP solution. So again, before we start with a set of columns that contains a primal feasible solution. So our start basis, so to say. And we want to extend it, and from there we want to get to an optimal LP solution. So what do we do here? We solve the LP for A prime, as we said before. We have the duals here. If you're lucky enough and we are converged, we can already stop. And then we do something else, as we did before. Here we add some columns with negative reduced cost from all the other columns. I don't say how we select them. We do it in some way. And then what the trick here is now, we take the duals that we got here from the LPs, and we put them in our Lagrangian. We put them here and here. As I said before, if they were the optimal duals, then it would actually also be an optimal solution to the Lagrangian. But we at least hope to expect, when they get closer and closer to the optimal, that this problem is very close to the actual problem we want to solve. And the nice thing is here, the solution to this problem always will have a path structure, because it's a network flow. So we will always have some kind of network there, which gives us path, right? So if we start to add part of the primal solution here, we kind of restrict ourselves to paths, and then we always add paths to the problem. So we kind of get a path structure. And the same here, right? So we have these two separate problems, which capture different aspects of the problem. And for each of them, we take some part of the primal solution, take the columns, and add them to our master problem. So it's basically a sifting, which is a bit more fancy and does takes care of the path. Of course, you could from the beginning just do something as in the classic column generation. You create paths beforehand and just say, okay, all my paths are variables. Would be the classic approach, and just have a huge problem and try to add paths there. The problem is it's not so easy to generate feasible paths because there are a lot of extra constraints. So this approach has a nice thing, as opposed to explicitly generating paths and adding them as variables, that is far more flexible. If you have more constraints and whatnot, you can still use the same approach. Okay, so that's what we did. This algorithm doesn't work out of the box on our problems, not so well. So we had to add a lot of additional tricks and techniques, which I'm not allowed to tell you, because my company is a bit secretive. But I can just tell you, it works well for very large cases. So the problem is here, the LP is the hard part. You have no chance to solve it with a simplex. You have primal or dual. Sometimes you can do it with up to a certain size. You can use a barrier from Cplex, Gurobi, Express, whatever. But if you have really hard problems, that doesn't work anymore. So you have no chance basically to solve the LP. But the nice thing is, in this case, once you're very big, this approach still works very nicely on our instances. So we are able to get an LP solution. And the good thing in this case is the LP solutions are usually very tight. So the LP value is very close, or often the same as the IP value. And it's not super difficult to get from the LP to the IP. So you have to run some primal heuristics on top, but it's not super hard. Okay, so what are the advantages? So it can be well adapted to more complex models. So if the modelers decide to add some more constraints or whatnot, you can still use a similar approach. As I said, it works well for very large problems. And another thing, what is very important is that the LP solution has fewer fractional variables. So if, for example, you run this with a commercial barrier, commercial IP solution on the entire problem, we cannot afford to do a crossover because that's too expensive. Then typically we have a lot of fractional variables. And from there, it's difficult to get to an IP solution. Because in the end, you do some kind of fancy rounding, right? All the IP solutions do some kind of, you round in a certain way. It's a bit more clever, but in the end, you do some kind of rounding to get from an LP solution to an IP solution. And if you have a lot of fractional variables, that becomes very difficult. So a very nice feature here is because you always work on a very small column set. Even if you solve this column set with a commercial barrier, the ones our master problems, we get a problem with fewer fractional variables. So from there, it's much easier to get to an IP solution. So that's another strong point of the formulation here. Okay, that was it for the Vickers scheduling. Now we do duty scheduling. So basically what we did now, we scheduled all our Vickers, and now we have to assign basically the drivers to the Vickers. So this would be the classic approach. We start to optimize the Vickers, and after we do that, we schedule what is called the duties. So one duty is what, for example, driver can do during the day. Actually, it's divided into two parts. No, it doesn't really matter. In the end, we just do our crew assignment. Yeah, so we want to add the drivers to the buses. So we want to say which driver drives which buses. Okay, so what makes this problem a bit difficult is that drivers can change buses during the day. So for example, what you see here is one single trip. And in the end, what we want to do, we have all our Vickers, and now we need to cover the Vickers with drivers, so with duties. There are a lot of rules on what you have to consider and whatnot, something like break time, maximum duty time, whatnot. There are a lot of constraints there. Just very high level, let's say we have this bus trip here, which starts at 11:10, stops at 12:30. The thing is, I actually never noticed this before, but buses often have these what is called relief times, which means that drivers leave a bus during the trip, and another driver comes in. It actually happens. I paid some attention to it in Berlin. It actually happens quite often that the driver just leaves the bus and another driver comes in. This is called a relief time, which makes the problem harder, because we have this trip here, but we kind of have to split it, because at a certain point, a driver can go somewhere else. So for example, a driver did this part, but now the driver goes to another bus or goes home, makes a break or whatnot, and a new driver comes in, which makes the problem harder because you have a lot of more possibilities what you can do. So if we look, for example, at this schedule here, so here we have two buses. We have the red bus, which does this service trip, and then this service trip and goes back. We have the green bus, which goes here. That looks more complicated, because, for example, let's say we can split this duty up here, and we have this relief time. Then we have this trip here. We have two relief times. So here the drivers can be changed. Then we have a lot of more possibilities. So the blue guys basically tell you how a duty is. So I could go here during the day and end here. For example, I would start here, do this service trip. Then I have the relief point here from another service trip. Go here, change again, do this one, and go back. So basically, we have a lot of possible paths that go through this graph, which makes this problem hard. So we have a lot of possible duties. The important thing is each duty is an ST path. So each duty can be written like that, but not all ST paths are duties, because we have a lot of additional constraints on there. So basically, we have to look at the ST paths here, and then we have to kind of filter them out, because not all of them are valid. And this makes the problem quite hard. So again, this is just a picture. That doesn't really matter, all the math stuff. The important thing is for each duty, so you would have a set of duties, which can be huge, could be exponential. Then you have to have some tasks that you can cover. And I will not explain everything in detail here. The important thing is that you have some kind of set partitioning constraints, which tells you basically each constraint is a task that you have to cover, as we saw before. All these split up part here. That would be all our tasks that we have to do, that we have to cover. These guys we have to cover, and then this we can do by our duties. And that's why you get these kind of huge set partitioning problems here, where we have, that's a classic scheduling problem, right? So that you have to cover a lot of these constraints. And then you have some extra constraints, which are written down in a very generic way. But the important thing is here, you have the duties. The duties have to cover all the tasks. You have some extra constraints. And yeah, this problem can be very big. And again, what we want to do is we want to solve it with some kind of column generation because we cannot afford to solve this here. And then there are two ways of doing this. So the classic approach is more that you do a dynamic column generation, which means you generate the duties on the fly. So each duty is a variable. You have in the pricing problems, you generate new duties, and then you add them to the master problem. Another approach that you can also do, which is not so nice from a mathematical point of view, it's a bit like, it's a bit brute force. You can also pre-generate the duties. So you can say, okay, in the beginning, we do a lot of fancy stuff to have a lot of duties. We filter them down, we cut them down, and then we have a lot of actual duties that we have and we want to add. But also in this case, you have to do column generation, but more on a sifting approach that we did before. So these are the two ways that I know that I use in industry, that you have this dynamic generation and then you have this more static generation with pre-generated columns. Okay, I will not really talk about how this is solved. It's again some kind of column generation approach. Then the main problem what we have here is what we did was, right, we solved the weakest first, so we have a weaker schedule, and then the second part is that we have the duties. I will just very shortly talk about this. But this is not so nice in practice because in the end, what you want to do, you want to optimize both together, right? So doing the duties is also expensive, right? Because depending on how many drivers you take, where you send them, it costs you also a lot of money. So ideally, you would like to optimize both together. You wouldn't like to do first the weakest and afterwards the duties, but you would do both of them together. Which unfortunately is a very hard problem. So I just want to mention this, that is also something we are currently working on, which is because it's quite difficult to really do this well. So I'm not sure that anyone does it really to optimality on big real-world instances. So we also use some kind of heuristics there, because you have these two very difficult NP hard problems, and basically you want to solve them together to optimality, and this is hard. And the thing is, if you're unlucky, even your weaker schedule might not even be feasible, because you might create a schedule, actually happens sometimes in practice, which cannot be covered by a driver, for example, because it's just too long, and then you would break certain rules, like for example, the maximum time a driver can drive. So then it's even, in some cases, even infeasible. So ideally, you would like to optimize both of them together. Just to mention, this is a hard problem. Okay, that was it for the technical part. Now I want to show a bit how optimization work at Optibus. That's why I'm actually here, to make some advertisement for Optibus. The thing before was more alibi stuff. Okay, so Optibus. So what is Optibus? It's a public transport company. Was founded in 2014. It's a SaaS company. Before I started Optibus, I didn't know what SaaS means. It means software as a service. And which basically means everything runs in the cloud. Which for the user, it means you don't have to install anything. You just open your browser and you can do everything in the browser. You can click around and whatnot. Actually, here what is nice, optimization is really a central component of the company, because in the end, all the bus companies, they want to save money. So it's important for them to really have a well-optimized solutions. And also, we run quite a few optimization problems. So per month, we run thousands of instances in the cloud. This is a nice thing. You can really see, because everything is in the cloud. So you really have an overview, how many customers are there, how many problems are actually solved, which kind of problems are solved. So this is one advantage of having this cloud platform. So we have several thousand, sometimes we have more than 10,000 problems that are solved per month. So it's, I would say, heavily used. Okay, how does it look from the outside for the customer? I'm from Zapier, right? I'm more used to this, that you have a shell, everything is black, you type something in, you solve it with Cplet, Gurobi, Skip, and then you get some numbers out. But people in industry don't like this, right? I mean, these are not so much tech people. They want to have something nice and colorful and where you can click around. So that's why this is actually a quite important part, that you have all this fancy platform. It is a huge thing. So there's a lot of stuff you can do, click around and export and statistics and whatnot. So most of the people at Optibus do these kind of things. There are actually very few that do the optimization. Most people are doing these nice, colorful things here. So how does it look for a customer, right? So the customer goes into the cloud, kind of imports their problems. So they create, either they load it in or they click it together here. So they have in the vehicles problem, for example, they say, okay, we have these trips that we want to cover. We have these vehicles. They can do this and that and whatnot. Yeah. Then the algorithms run in the background. And at the end, the solution is shown. Yeah. And then the solution is the solution. Honestly, I'm not sure which kind of problem this is, but yeah. So you get some kind of nice, colorful picture, and the customers really like it. Looks nice, at least. I couldn't really tell you, to be honest, what exactly happens here, but it's something. Yeah, I think it's some bus schedules here that run there. Yeah, but this is the thing, right? I mean, I come more from academic world, right? If we do optimization, it's always like, yeah, we want to solve the optimization problem, but this is for the customers, it's certainly not enough, right? They want to have this huge thing around there, which does a lot of different stuff, and this is very important. Yeah. Okay, and how does it look in the background? Yeah, so typically what we have the customer, which has this web interface. Click something together here. So then we have the first layer, it goes down, it's the modeling part. So this is really separated for us. So we have this modeling people, which are actually far more modeling people than I would say solver people, which also makes sense because these formulations are really difficult. Yeah, so what you saw before is quite simple, but in the real world, you have a lot of extra constraints, which makes this much harder. Also, the modeling part is quite hard because you have to consider so many different things. So this is really hard to do that. That's why many people do that, Optibus. So what they do here is, okay, they get this, they get the customer data, and from there they build a mathematical model, basically something like a MIP, which is not a pure MIP, it's a MIP with some metadata. So here the MIP is created with some additional data that we have, and then it's handed down to where I work in the very low part. And here we have what we call the engine. So in the end, it's some kind of specialized MIP solver. It's really surprisingly detached from everything else, right? I mean, we use some problem-specific data, but not so much. So it's not super tailored to the actual problem. So the advantage is that you can solve a lot of different models with that, and that's also easy for the modelers to extend it. Of course, it's harder to get the same speed that more really specialized approaches have, but the nice thing is quite generic. So it's some kind of a MIP solver, which of course uses some problem-specific data, but it's not absolutely tailored to the problem. It's a bit more independent. So then we have this specialized MIP solver here, which solves the problem. The solution goes back to the mathematical modeling part here, so the modeling layer, and they take the solution and then they create some schedule out of it, which goes into the web interface where you have these nice colorful pictures for the customers. And yeah, I work here, and it's surprising. In the end, we have only, I would say, 2 people that really work on this part here, which one of them is me. We have also one colleague that works a bit on that, but there are far more people that work in this modeling part. There are far more people in the entire company. So even though the optimization is an important part, there are not so many people working on this because it takes far more time to build all the stuff around this. Okay, then just let's mention some challenges that we have here. As I said before, the models are really far more complex than we see here. There's a lot of details, a lot of things that you have to consider. Luckily, I don't really have to deal with this. The modeling people have to do that. Another thing that the models can be huge. So for the vehicle problems we saw before, we often have problems with tens of millions of variables. So really huge problems with which you have no chance to solve them with the commercial solver. If you put them into a Gurobi or Express or something, you cannot solve them. And then also another challenge is that now we have a lot of electric vehicles that come in, which makes the models far harder. So this is kind of the new challenge here that we have to cover electric vehicles, because you have to have something like charging and whatnot, and that makes everything more complicated. Okay, that was it. Thank you.